You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Training is the stage where artificial intelligence models learn to recognize patterns and relationships in data. In essence, training is the process of adjusting internal parameters, often referred to as weights, so that predictions align more closely with known outcomes. When data flows through a model, the system produces an output that is compared against the true answer. The difference between the prediction and the actual value generates an error, which is then used to adjust the weights in a direction that reduces future errors. This process, repeated thousands or millions of times, gradually tunes the model's parameters until it becomes capable of mapping inputs to outputs reliably. Training transforms a model from a collection of equations and structures into an intelligent system capable of performing tasks such as classification, prediction, or decision-making. For learners, it helps to think of training as the educational phase, where data serves as the teacher guiding the model's progress. Training data serves as the backbone of supervised learning, providing the labeled examples that drive the learning process. Each record in a training dataset contains an input paired with the correct output, allowing the model to study how the two relate. For example, in an email spam filter, the training data may include thousands of emails marked as either spam or not spam. By examining these labeled examples, the system learns which words, phrases, or structures are most associated with unwanted messages. The quality and diversity of training data directly determine the strength of the model. If the training set is biased or incomplete, the model will inherit those flaws, performing poorly in real-world conditions. This illustrates the broader principle that AI models are only as good as the data that teaches them. High-quality training data provides the foundation for accurate and trustworthy predictions. The process of learning during training is iterative, refining predictions across multiple passes through the data, known as epochs. In each epoch, the model evaluates every example in the training set, updates its weights based on errors, and begins another cycle with slightly improved parameters. Over time, the cumulative effect of these repeated adjustments is a gradual convergence toward accuracy. This mirrors human learning, where repeated exposure to concepts or problems deepens understanding. For example, a child learning multiplication does not master it after a single lesson, but improves with practice over many repetitions. Similarly, an AI model's capacity grows through multiple epochs, where it repeatedly confronts the data and reshapes its internal parameters. This iterative cycle underscores that training is not instantaneous, but a process of continual refinement, with each pass bringing the model closer to reliable performance. Overfitting represents one of the most common problems during training. A model is overfitted when it memorizes the training data so thoroughly that it loses the ability to generalize to new examples. Imagine a student who memorizes answers to practice questions but cannot solve slightly different problems on the exam. Overfitted models may achieve high accuracy during training, but perform poorly when tested on unfamiliar data. This happens when the model captures noise or random quirks in the training set rather than the underlying patterns. For instance, a vision model trained only on clear, well-lit images of cats may fail when presented with a blurry photo because it never learned the essential features of catness. Overfitting highlights why training alone is not enough. Validation and testing are necessary to check whether a model has learned generalizable rules rather than memorizing specifics. Underfitting is the opposite problem, occurring when a model fails to capture the essential patterns in the data. An underfitted model performs poorly not only on new, unseen data, but also on the training set itself. This typically arises when the model is too simple for the task, lacks sufficient training time, or is constrained by overly strict assumptions. For example, trying to fit a straight line to data that clearly follows a curve will leave large errors unaddressed. Underfitting shows that effective models require both enough complexity to capture patterns and enough exposure to data to refine their learning. For learners, underfitting illustrates the importance of balance in model design. Too little capacity or too little training leads to shallow, ineffective learning, just as an oversimplified study guide cannot prepare a student for a complex exam. Validation plays a vital role in monitoring learning during training. Unlike training data, which directly teaches the model, validation data is kept separate and used to check performance as the model improves. It acts as a checkpoint, showing whether the system is learning patterns that generalize beyond the examples it has seen. Validation results inform critical decisions about when to stop training, which parameters to adjust, and how to prevent overfitting. For example, if validation accuracy improves at first, but then begins to decline while training accuracy continues to rise, this signals overfitting. Validation is the stage where learning is tested in progress, offering feedback about how well the model might perform in the real world. For learners, it helps to think of validation as the practice exam that gives feedback during study, guiding adjustments before the final test. Hyperparameter tuning is one of the key ways validation data informs improvement. Unlike model parameters, which are learned during training, hyperparameters are settings chosen by developers before training begins. They include factors such as learning rate, which controls how aggressively weights are adjusted, or the number of layers and nodes in a neural network. The wrong settings can lead to underfitting, overfitting, or unstable training, while the right ones enable smooth convergence. Validation data provides the feedback needed to test different configurations systematically. For instance, running multiple experiments with different learning rates allows practitioners to select the value that yields the best balance of accuracy and stability. Hyperparameter tuning illustrates the trial-and-error nature of AI development, where careful experimentation guided by validation results refines performance. It shows that success depends not only on algorithms and data, but also on well-chosen settings. Cross-validation is a technique designed to make evaluation more reliable by splitting data into multiple subsets or folds, and rotating which subset is used for validation. In k-fold cross-validation, the dataset is divided into k parts, and the model is trained k times, each time using a different fold as validation, while the others serve as training. The results are then averaged to provide a robust measure of performance. This method reduces the risk that outcomes are skewed by an unusual split of the data. For example, if a dataset happens to cluster certain patterns in one subset, a single validation split may misrepresent model quality. Cross-validation ensures that every record is used for both training and validation at some point, making evaluation more comprehensive. For learners, cross-validation demonstrates the importance of fairness and thoroughness in preparation, ensuring that models are tested against the full diversity of their data. Early stopping is another safeguard against overfitting, using validation results to decide when to halt training. As training progresses, accuracy on the validation set typically improves to a point but may begin to plateau or even decline if the model starts memorizing noise. Early stopping monitors this curve, freezing the model at the point of best generalization. For instance, if after 20 epochs validation accuracy peaks but declines during further training, early stopping preserves the best version of the model rather than allowing overfitting to continue. This approach saves computational resources and produces stronger models. It mirrors human study habits, where over-repetition can lead to fatigue or confusion rather than deeper understanding. For learners, early stopping shows how monitoring feedback in real time helps optimize effort, preventing wasted computation, while capturing the optimal balance between memorization and adaptability. Testing is the final stage of evaluation, where a fully trained and validated model is applied to an unseen dataset to measure performance objectively. Unlike training and validation sets, test data is held back entirely until this stage, ensuring that results reflect genuine generalization. Testing provides an unbiased estimate of how the model will perform in real-world conditions. For example, an AI medical diagnostic tool may be tested on patient records from hospitals not included in the training process, providing confidence that its predictions apply beyond the development environment. Testing is akin to the final exam. While training is the studying phase and validation is the practice test, testing determines whether the preparation translates into real capability. For learners, it underscores why discipline in data separation is critical. Without it, performance claims cannot be trusted. It is essential to distinguish between validation and testing, as their purposes are complementary but distinct. Validation is used during training to guide adjustments, fine-tune hyperparameters, and prevent overfitting. Testing, in contrast, is reserved until the end, providing a final, unbiased assessment of performance. Confusing these roles can lead to subtle errors. If test data is used during validation, results may be overly optimistic, giving the illusion of reliability when the model has actually seen hints of the test set. This issue, known as data leakage, undermines trust. The separation of validation and testing emphasizes the discipline required in AI development, where proper boundaries ensure that evaluation reflects reality rather than hidden shortcuts. For learners, this distinction clarifies why multiple datasets are necessary and why their careful use determines the credibility of results. Data separation, therefore, is one of the most important principles in training, validation, and testing. Without it, models risk exposure to information they should not have, leading to inflated performance metrics that collapse in practice. Separating data ensures that training examples do not overlap with validation or test sets, guarding against leakage. For example, if duplicate patient records appear in both training and testing datasets, a medical model may achieve artificially high accuracy by recognizing repeats rather than learning genuine diagnostic patterns. Proper separation prevents such pitfalls, guaranteeing that performance reflects true learning. For learners, this principle highlights the rigor AI requires. Just as scientific experiments demand controls and unbiased samples, AI development depends on strict boundaries between training, validation, and testing to produce credible, reproducible outcomes. Evaluating models requires performance metrics tailored to the task at hand. For classification problems, accuracy measures overall correctness, while precision and recall highlight different aspects of performance. Precision focuses on how many predicted positives are truly correct, while recall measures how many actual positives the model successfully identifies. The F1 score balances the two, providing a harmonic mean that rewards models excelling in both areas. For instance, in spam detection, precision measures how often flagged emails are truly spam, while recall measures how many spam emails were successfully caught. Each metric captures a different perspective, reminding practitioners that no single measure fully describes performance. For learners, metrics illustrate that evaluation is nuanced. A model that appears accurate overall may still fail critically if it misclassifies rare but important cases, showing why multiple measures are essential. Receiver operating characteristic curves, or ROC curves, and the area under the curve, or AUC, provide tools for evaluating classification models across different thresholds. Instead of choosing a single cutoff for deciding positive or negative, ROC curves plot the trade-off between true positives and false positives across all possible thresholds. AUC summarizes this curve into a single number, with values closer to 1 indicating stronger performance. These tools are especially useful when classes are imbalanced, as they show how models behave beyond simple accuracy. For example, in fraud detection, a model may achieve high accuracy by predicting not fraud most of the time, but ROC curves reveal whether it distinguishes rare fraud cases effectively. For learners, ROC and AUC demonstrate how visualization and holistic evaluation provide deeper insight than raw numbers alone. Regression tasks, which involve predicting continuous values rather than discrete categories, require their own set of metrics. Mean squared error calculates the average of squared differences between predictions and true values, penalizing large deviations heavily. Mean absolute error provides a simpler average of absolute differences, offering a more interpretable measure of error magnitude. The coefficient of determination, or R-squared, evaluates how well predictions explain the variance in the data, with values closer to 1 indicating strong explanatory power. For example, in predicting housing prices, mean squared error highlights extreme misses, mean absolute error shows typical error size, and R-squared reflects overall model fit. Each metric provides a different lens, ensuring evaluation covers both accuracy and explanatory ability. For learners, regression metrics highlight the diversity of evaluation methods, emphasizing that each model must be judged according to the nature of its predictions. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. One of the most important concepts in model development is the bias-variance trade-off. Bias occurs when a model is too simple, making strong assumptions that prevent it from capturing the complexity of the data. Variance, on the other hand, arises when a model is too complex, fitting the training data so closely that it struggles to generalize to new cases. Balancing bias and variance is essential to building models that are both accurate and adaptable. High bias leads to underfitting, where the model performs poorly on both training and unseen data. High variance results in overfitting, where the model excels on training examples but fails on new ones. The ideal balance lies somewhere in the middle, where the model is complex enough to capture true patterns but simple enough to avoid memorizing noise. For learners, this trade-off illustrates that model development is not about maximizing complexity, but about finding the sweet spot where learning is both accurate and reliable. Regularization techniques are used to manage complexity and prevent overfitting. L1 regularization, often called lasso, penalizes the absolute value of weights, encouraging sparsity by pushing some coefficients to zero. This effectively simplifies the model by removing less important features. L2 regularization, known as ridge, penalizes the square of weights, discouraging large values without eliminating them completely. Dropout, a method widely used in deep learning, randomly disables a portion of neurons during training, forcing the network to learn redundant pathways rather than relying on specific nodes. Each of these strategies reduces variance and improves generalization, ensuring the model performs well on unseen data. For example, a deep neural network trained on thousands of images may memorize small details without dropout, but will learn more robust patterns when dropout is applied. For learners, regularization highlights that effective training is about guiding models to focus on essentials while ignoring noise. Data augmentation is another way to improve generalization by expanding the diversity of training datasets. Instead of collecting entirely new data, augmentation generates variations of existing examples. In computer vision, this might involve rotating, flipping, or adjusting the brightness of images. In text analysis, augmentation could involve paraphrasing sentences or replacing words with synonyms. In audio tasks, adding background noise or shifting pitch can create useful variety. These techniques prevent models from overfitting by exposing them to a wider range of conditions, forcing them to learn general features rather than memorizing specifics. For example, an image recognition model trained with augmented data will be better able to recognize objects in different lighting or orientations. Data augmentation demonstrates that preparation continues even during training, enriching datasets to build stronger, more flexible models. For learners, it emphasizes creativity in preparation as a critical factor in AI success. Ensemble methods strengthen performance by combining multiple models into a single system. Instead of relying on one model's predictions, ensemble approaches aggregate the outputs of several, reducing the impact of weaknesses in any individual. Bagging, or bootstrap aggregation, trains models on different subsets of the data and averages their results, improving stability. Boosting trains models sequentially, with each new model focusing on correcting the errors of the previous ones, producing highly accurate results. Random forests, a popular ensemble method, combine many decision trees to balance accuracy with robustness. For example, while one tree may misclassify a case, the majority vote of hundreds provides a more reliable outcome. Ensembles often outperform single models, especially in competitions and real-world applications. For learners, ensemble methods show that diversity is strength. Combining perspectives, whether human or algorithmic, leads to more accurate and dependable decisions. Validation in deep learning has its own unique practices due to the scale and complexity of models. Validation losses are monitored closely, providing real-time signals of whether training is improving or beginning to overfit. Checkpoints are saved periodically, capturing versions of the model at different stages so the best one can be preserved. Hyperparameter sweeps test many different configurations, such as layer sizes, learning rates, or activation functions guided by validation performance. These practices reflect the experimental nature of deep learning, where small adjustments can lead to large differences in outcomes. For instance, choosing a slightly higher learning rate might cause unstable training, while a lower one may slow progress. Validation provides the feedback loop necessary to navigate these sensitivities. For learners, it illustrates how iterative experimentation, guided by careful validation, is the engine of progress in training large, complex models. Automated machine learning, or AutoML, represents an effort to streamline and accelerate training and validation. AutoML platforms automate tasks such as model selection, hyperparameter tuning, and feature engineering, reducing the need for extensive manual experimentation. These systems evaluate many different approaches systematically, choosing configurations that maximize performance on validation data. For example, an AutoML system might test dozens of algorithms on a dataset, rank their results, and deliver the best-performing model with minimal human intervention. While AutoML does not replace human expertise, it still requires careful interpretation of results. It democratizes AI development by lowering technical barriers. For learners, AutoML demonstrates how automation can empower practitioners to focus on higher-level goals, such as defining problems and ensuring fairness, while leaving repetitive optimization tasks to software. It highlights the growing synergy between human oversight and machine-driven experimentation in AI development. Testing plays a decisive role in preparing models for deployment. It ensures that systems perform reliably when applied to real-world scenarios, where conditions often differ from training environments. Testing involves applying the final model to a set of unseen data that simulates deployment as closely as possible. For instance, a speech recognition model trained on studio-quality recordings must be tested on noisy, real-world audio to ensure robustness. Testing provides confidence that performance metrics reflect genuine capability rather than artifacts of data or training. Without rigorous testing, models risk failing when deployed, undermining trust and utility. For learners, testing highlights the difference between development and application. A model that looks strong in the lab may falter in the wild, making thorough evaluation essential before releasing AI into practice. Stress testing extends evaluation by challenging models with edge cases and adversarial inputs. These tests go beyond typical scenarios to probe robustness under unusual or hostile conditions. For example, image recognition models may be tested with distorted or adversarially altered images to see if they still classify correctly. Financial models may be exposed to extreme market scenarios to ensure stability. Stress testing reveals vulnerabilities that may not appear in ordinary validation or testing, preparing models for the unpredictability of real-world use. For learners, stress testing shows that evaluation is not just about averages, it is about resilience. Robust AI must withstand unusual conditions, not just perform well on typical cases. This principle emphasizes the importance of designing systems that remain reliable even under pressure. Fairness testing is another dimension of evaluation, ensuring that models perform equitably across demographic groups and contexts. Bias can creep in through unbalanced training data, leading to models that excel for some groups while failing for others. For example, a facial recognition model may perform well on lighter-skinned individuals, but poorly on darker-skinned individuals if training data was skewed. Fairness testing involves systematically evaluating performance across subgroups and identifying disparities. Corrective actions may include rebalancing data, adjusting algorithms, or refining objectives. Fairness testing reflects the ethical responsibility of AI development. Accuracy is not sufficient if it comes at the expense of equity. For learners, this underscores the importance of considering not just whether a model works, but whether it works fairly for everyone it affects. Interpretability plays a growing role in validation, providing insight into how models reach their conclusions. Complex models, particularly deep learning systems, often function as black boxes, making it difficult to understand why they produce particular outputs. Explainable AI methods, such as feature importance rankings, saliency maps, or surrogate models, help reveal the reasoning process. Interpretability aids in diagnosing problems. If a model classifies images based on background colors rather than objects, interpretability tools can expose this flaw. It also builds trust, allowing stakeholders to see not just outcomes but the reasoning behind them. For learners, interpretability demonstrates that validation is not only about measuring accuracy, but also about understanding decision-making, ensuring that models behave in ways aligned with human expectations and ethical standards. Continuous evaluation acknowledges that model performance can drift after deployment. Real-world environments change, customer behavior evolves, language use shifts, and external conditions fluctuate. A model that once performed well may degrade over time if not updated. Continuous monitoring tracks key metrics in production, detecting when accuracy declines or biases emerge. Feedback loops allow models to be retrained periodically with new data, maintaining relevance. For example, recommendation systems must adapt constantly as user preferences shift. Continuous evaluation shows that validation and testing are not single events, but ongoing responsibilities. For learners, it illustrates the lifecycle nature of AI. Models must be maintained and evaluated throughout their operation, not just at launch. Reproducibility is a cornerstone of trustworthy AI development, ensuring that training and testing results can be independently verified. Practices such as fixing random seeds, versioning data, and documenting pre-processing steps make it possible to replicate experiments consistently. Without reproducibility, models may appear to perform well due to chance or hidden biases, undermining credibility. For example, if two teams cannot reproduce each other's results on the same dataset, confidence in the findings diminishes. Reproducibility supports scientific integrity and fosters collaboration, allowing researchers to build upon each other's work. For learners, reproducibility emphasizes that rigor in AI is not only about performance, but also about transparency and accountability, ensuring that claims can be tested and verified. Human oversight remains essential, even in advanced evaluation frameworks. Domain experts bring contextual knowledge that algorithms cannot replicate, ensuring that validation and testing align with real-world goals. In healthcare, doctors review AI diagnostic systems to confirm that outputs are clinically meaningful. In finance, analysts check whether predictive models align with regulatory requirements and practical constraints. Human review adds nuance, identifying issues that metrics alone may miss. It also introduces accountability, ensuring that decisions affecting people's lives are not left entirely to machines. For learners, human oversight demonstrates that AI development is not an isolated technical exercise, but a collaborative process where expertise, ethics, and responsibility guide evaluation and deployment. Training and evaluation at scale demand significant computational and energy resources, shaping how and where AI systems are developed. Large-scale models with billions of parameters require extensive GPU clusters, terabytes of storage, and weeks of training. These resource demands increase costs and raise concerns about environmental impact. Practitioners must balance ambition with efficiency, optimizing algorithms and infrastructure to reduce waste. For example, using transfer learning allows teams to fine-tune existing models rather than training new ones from scratch, saving time and energy. For learners, resource considerations highlight that building AI is not only about accuracy, but also about sustainability and accessibility. The choices made in training and testing affect who can participate in AI development and how its benefits are distributed. The life cycle of model development reinforces that training, validation, and testing are not isolated stages but repeating cycles. A model may be trained, validated, and tested, then retrained with augmented data, revalidated with new configurations, and retested for deployment. This iterative process reflects the evolving nature of AI, where systems improve through repeated cycles of refinement. Each round deepens generalization, strengthens reliability, and addresses emerging challenges. For learners, this lifecycle highlights that evaluation is not an afterthought but a continuous practice embedded in AI development. It ensures that models remain accurate, fair, and trustworthy over time, adapting as data, environments, and goals evolve. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.